So just a final word on this idea of the set of possible derivations. So remember, y of x is the set of valid derivations for particular input sentence x. This will, in general, be exponential in size. Or a little more precisely, the number of elements or the number of valid derivations is going to grow exponentially fast with respect to the sentence length. Okay, that's a usual observation. So this is going to be a very, very large set of possible derivations. Okay, so we're almost there with the definition of the decoding problem for phrase-based models. The final definition is the following. So for a given sentence x, again x is going to be some sequence of words x1 through xn. This is going to be some German sentence in our particular examples. We generate from this a set of valid derivations, so each of these is going to be a sequence of phrases. Okay. And this set, as I said before, could be extremely large. And the translation problem is going to be to try to find the derivation in this set which has the highest score under some function f of y. Okay, and fy is, roughly speaking, something like log p of y, p of x given y, where this is a trigram language model, and this is the translation model. I say roughly speaking because it's actually questionable whether phrase-based models, as we'll define them, really rigorously define a model of this form, but that's roughly the intuition. Okay, but a good translation, remember y is going to be a derivation, is going to both have good probability under a trigram language model and also have good probability under this translation model. But let's be absolutely explicit about what f of y is. So if we score a derivation, we're going to take into account three terms. And again, I'm going to give the abstract definition here. We'll go into this in considerable detail in the next slide with an example. But the three terms are the following. So firstly, remember e of y is the sequence of words in the translation. So this could, for example, be we must also take these criticisms seriously. And h of e of y is just going to be the score under a trigram language model. Okay, so this score h is going to score our English sentence. Sorry, this is maybe not so clear, but this is an English sequence of words. This is going to be actually the log probability under a trigram language model score. Okay, second term. So now remember, our derivation y consists of a sequence of phrases p1, p2, up to pl. Each of these phrases is going to have some score, and so g of p1, for example, might be the score for the first phrase, might be minus 2.3 or something. And we're going to sum up the scores for the individual phrases. Okay, so that's the second part of the score. And then finally, we're going to have what's called a distortion score. So in addition to the strict limit on distortion distances, as I showed you on the previous slides, we're actually going to have a cost associated with distortions. So we're going to take eta times this distance that we calculated before, basically the distance between each phrase and the next phrase. And eta is some parameter that's typically negative, which penalizes reorderings, so penalizes large values for this difference between two phrases. So eta is typically negative. It might take some value like -1 or -2 or something like this. And it's typically chosen to optimize translation performance. Okay, so there are various ways to choose eta in a way that optimizes translation quality. Okay, let's look at how this expression is calculated using a particular example. So this is the definition of f of y. And the decoding problem is going to be to try to find the derivation that maximizes the sum of these three different scores. Okay, so let's illustrate this with an example. This is our input sentence. This is one possible derivation, y, and I'm going to calculate f of y, which is going to be the score for this particular derivation. Okay, so, and as I said, this is going to consist of a sum of three terms. A language model score. So first we have the language model. Secondly, we have what are called the phrase scores. And finally, we have the distortion scores. Okay, so let's go through these in turn. So firstly, the language model. So I'm going to have a sum of terms. So firstly, I'm going to have log of q of we given star star. And then I'm going to have log of must given star we, because must is the second word in this translation. And then log of also given we must. And then log of take given must also. And so on and so on. So this is because under this derivation, the translation is we must also take this criticism seriously. And so I have basically a sum of terms. In each case, I take the trigram parameter, I take its log, and I sum together all of these logs. Okay, so that's the language model score. And again, this is going to reflect how likely this final translation is as a sentence of English. So we're making critical use of a language model in scoring this derivation as to how plausible a sentence of English it is. So that's the first component. Now let's look at the phrase scores. So now I'm going to have a set of terms. So G of 1, 3, we must also, plus G of 7, 7 take, plus G of 4, 5 this criticism, and so on and so on. So remember, G was a function that takes a phrase and gives it a score, typically a log probability. And again, we're going to have one of these G terms for each of these phrases. So the 1, 2, 3, 4 phrases, we're going to have 4 G terms. So that's the phrase scores. Finally, let's look at how the distortion scores are scored for this particular example. Okay, so I'm going to go through each phrase in turn, looking at how far it is from the previous phrase. So the first thing we're going to do is look at the start point of this first phrase, and just look at 1 minus 1, this absolute value, times eta. So that corresponds to, there's this first term, which is basically eta times 1 minus s of p1. So this is penalizing how far the first phrase is from the very start of the German sentence. This is actually 0 in this case. And then let's look at the next term. So now I'm going to compare 3 to 7, the end of this phrase, to the start of this one. And I'm going to take 3 plus 1 minus 7, take its absolute value, times eta. Okay. And then I'm going to look at 7 versus 4. So I'm going to look at 7 plus 1 minus 4 times eta. And then 5 versus 6. So 5 plus 1 minus 6 times eta. And again, eta might take some negative value. For example, eta equals minus 1, typically chosen to optimize the performance of the translation model. So you can see that these terms are basically going to give penalties whenever we see a distortion that's non-zero. So this is 0, this is 0. I think this value is 3, and this value is 4. And so the final cost in this case is 7 times eta as the final distortion cost for this particular example. Okay, but to jump to back to the high level, we have a sum of 3 different types of scores: language model, phrase scores, and distortion scores. The language model scores how likely the resulting translation is as a sentence of English. The phrase scores can be thought of as a measure of how well these English phrases match the underlying German. For example, how well "we must also" matches "wir müssen auch." And then finally, these distortion scores penalize phrases moving long distances in these translations.